this Zoom. So shall I announce you?
Sure.
It's a great pleasure to welcome Andrea Appel from the University of Parma, and he will talk about the R matrix of the affine Yangian.
Thanks a lot, Bart, for the introduction. Thanks all the organizer for this invitation. It's a pleasure to speak at this seminar. And this is actually the first time I get to talk about this paper. So as you know, this is like even the seminar somehow it's a work in progress. So anyway, this is the first attempt. Okay, so let me start first by briefly recalling what the situation is and essentially what the content of the title is for the standard Yangian, let's say for the Yangian of finite type. So what is the construction of the R matrix for the Yangian of finite type? So as everyone, this is the integrable system seminar, so some stuff probably is not necessary to be recalled, but just to be precise, let me say everything. So an R matrix clearly is an operator that satisfies the Famous-Yang-Baxter equation. This is this equation that you see here. So generally, what I will consider as an R matrix in this case would be an operator on a tensor product of a vector space V. And this operator actually will be, in fact, somewhat like either a function or a formal power series, which is valued in endomorphism of this tensor product, V tensor V. And then the Yang-Baxter equation is this identity here that should be read in as taking values in end of V tensor V, so in the triple tensor power. So the Yangian, as was introduced by Drinfeld in 1985, was indeed like a way of producing rational solution of the Yang-Baxter equation in somewhat systematic way, as we know through its representation theory. So in particular, by considering this very big algebra and then finite dimensional modulo over this algebra, then in particular on irreducible representations, there will be a rational operator. So let me remind you briefly how this story goes. So we start with A being a finite dimensional simple Lie algebra, a complex simple Lie algebra for the moment, and H bar to be in fact a numerical deformation parameter. So as we will see, at least this first part of the story, H bar can be either a formal deformation parameter, so everything can be thought to live over formal power series in H bar, or in fact as a numerical value. The second part, which will be indeed about the content of our results with Sachin and Curtis, which I forgot to mention at the beginning, is in fact valid only for numerical values. So this will be my setting from now on. So we fix this deformation parameter H bar, and then the Yangian of A in fact is what? So we are starting again with a finite dimensional simple Lie algebra, and then in this case, basically Drinfeld proved that if I consider the current algebra AZ, so here I'm just considering polynomial functions with values in A, and then I have the standard Lie algebra structure, and then I consider the enveloping algebra of this very big algebra, this very big Lie algebra. Then, of course, the enveloping algebra is an off algebra, and this off algebra has in fact sort of a canonical deformation. So by imposing some homogeneity in the structure of the deformation, one can actually identify and characterize the Yangian of A as somewhat a canonical object. And then, as I will mention in a second, of course, this canonical object then can be constructed via presentation. The Yangian, for the moment, being a black box, going to details presentation of the Yangian and the relation of the Yangian with all the all the various flavor. But I will use it mostly as a sort of a black box. This is somewhat an object that has this role in life, which is again to canonically quantize the enveloping algebra of the currently algebra. Anyway, so as being an off algebra, the Yangian is equipped with a coproduct, which we denote by delta. And in fact, as this is, as I said, this is a quantization of the current algebra. One of the most interesting features of the Yangian is that it is equipped with a one-parameter subgroup of algebra automorphism. What is this and how it is defined, what it does? Well, simply this can be thought as being a quantization of the usual shift for the currently algebra. So I just take the parameter z and then I shift it by s. And then this standard automorphism at the classical level, they admit this quantization for the Yangian. Now, by relying on this shift operator, this one parameter subgroup of automorphism, which again, keep in mind, they preserve the full of algebra structure. Then we can actually consider a sort of a modified version of the
Andrea, can I ask you a question?
Sure, go on.
Sorry to interrupt. I'm just kind of a wider question.
Mm-hmm.
What is the classification of all Hopf algebra automorphisms of the Yangian? Can you remind me?
You mean?
Is it not known?
Oh, that one I don't know. I'm not sure.
I mean, you have like
known,
diagram automorphisms, and maybe more. I don't know.
Well, again, no, I think it's a little bit more complicated. So, in a certain sense, yeah, for the question you have in mind, for example, I mean, again, I will say it in a second. It's like if you consider Greenfeld presentation of the Yangian, which is very much like a Kac-Moody sort of presentation, then you may use the diagram automorphism scheme and so on. And then in that case, on the other end, like knowing how the coproduct is sort of quite complicated, right? So you don't have explicit expression. So for example, I think I'm assuming that actually maybe using that classification here is a little bit more, it's a little bit trickier. But anyway, the short answer is I don't know precisely what the classification is. So it's a good point. Okay, so anyway, so I was saying here I can consider this sort of modification of the coproduct, in which essentially I apply the coproduct, I go into this tensor product of the Yangian, and then I shift one of the leg. Actually, I shift the left leg. This is the convention we use here. So we shift the left leg, and then we consider the opposite coproduct, which again is the flip, is the opposite coproduct, and then again I'm shifting the same left leg. So this is the definition. And so the theorem of Greenfeld was about the existence of the R matrix for the Yangian of finite type was the following. So there exists a unique formal series in a parameter S inverse. So this formal series, which I'm denoting by RD, so this would denote hereafter the Greenfeld R matrix. So clearly there is a normalization condition. This operator starts by 1, and then you have the other terms, the other higher order terms in S inverse. Again, this is a formal object, but it's still an algebraic object. All the term in this series, of course, lives in this tensor product. Okay, and this formal series satisfy the usual identity you would expect from the R matrix. So we have an intertwining equation here, in which the R matrix is actually moving is clearly relating the opposite coproduct with the usual coproduct, and then you have the cabling identity, so the coproduct identities that tell you how this operator works if you apply the coproduct to one of the leg of this formal series. Now you should note immediately that here actually there is already something which is a little bit unbalanced, right? The intertwining equation is really defined in terms of this twisted tensor product. Let's say shifted coproduct, right? I have this delta S here, while on the other end, the cabling identities, the coproduct identity that I'm writing here are in fact written only for the usual coproduct without extra parameter. Of course, I can take this identity and throw in again the shift on one of the leg, and then you will introduce into this equation a second parameter that corresponds to the shift, and so you will get a more complicated identity. And then by combining these two, again, one gets that this operator Rd in fact satisfy the Yang-Baxter equation, the usual Yang-Baxter equation, which indeed perform here two parameters, S1 and S2. So this is how in the Gabling identities, by shifting one of the leg, one will perform also the appearance of the second parameter, and then one can obtain this equation. Okay, so this in a certain sense is probably it's quite it's very well known result, and it produces somewhat a perfect parallel with the story of quantum groups, of Drinfeld-Jimbo quantum groups and their universal R matrix, and how that story applies to the affine case when I go and consider quantum affine algebra. On the other hand, there is a very big difference here. So in the case of the quantum group, as we all know, the R matrix comes from this universal object, which at the same time is characterized by the fact that it performs the pairing. Is the canonical object encoding the pairing between the positive Borel and the negative Borel. Drinfeld construction of the R matrix, on the other hand, for the Yangian was very different. So in fact, the proof that Drinfeld gave was a cohomological proof. So the construction of the R matrix in this case is absolutely not explicit, and also it's very, very, very much attached to the fact that we are considering a simple Lie algebra. So we started from A being a finite dimensional simple Lie algebra, and so clearly this is why this cohomological argument can be applied, and they work. And this also is the same motivation behind the fact that one can in fact characterize the Yangian as being a canonical quantization of the current algebra. So all this statement really relies a lot on the fact that we started from a simple finite dimensional simple Lie algebra at the beginning. Okay, so nonetheless, being such a not an explicit object, what we can do is that still take these operators, which we said already is an algebraic operator, still a formal series with values in the algebra, and then apply it on a kappa pair of finite dimensional irreducible representation. And this instead is more or less the usual gist that we have also for quantum affine algebra. So what we do in this case, we consider V1, V2 to finite dimensional irreducible representation of the Yangian. And we can take therefore our universal operator RDS and evaluate it on this tensor product V1 tensor V2. Now, these are finite dimensional irreducible representations, so one can prove as a usual result that these are generated by a highest weight vector. You can fix two highest weight vector V1 and V2, look at the action of this R matrix, and then you will see that this action now is acting diagonally on this tensor product. This produces a scalar. I can normalize this operator by the scalar, and this is producing an operator bold R, which is in fact is a rational operator in S and satisfies some sort of unitarity condition. So this is actually the usual result that one can imagine, and this is the way that we can produce on any finite dimension irreducible representation. We are able to produce a solution of a rational solution of the Yang-Baxter equation. So this more or less was the story already in the 80s, as was proved already in the 80s. Okay, so as I mentioned, on the other end, even though I'm really putting a lot of stuff under the carpet, but as I mentioned, the Yangian has somewhat black box presentation, black box characterization as a canonical quantization, but at the same time, one of the best feature of this algebra is that it possesses a lot of ways of being presented. So the original presentation in quote was the so-called J presentation. This way of presenting the Yangian was very useful, in fact, to give it an off-algebra structure. So the coproduct is actually expressed and proved to exist in this presentation. And then at the same time, there was at some point Drinfeld introduced another presentation, so-called the Drinfeld new presentation, which is somewhat a loop presentation, which is what I was mentioning before with Bart. This loop presentation is somewhat instead, loop or current presentation is instead much easier to generalize to different Lie algebras, essentially. Move the level from finite dimensional simple Lie algebra to, for example, symmetrizable Kac-Moody. Why is it so? Because this loop presentation, in fact, is given simply as I give you a Cartan matrix and then you give me back an algebra by generators and relation. And all these relations are actually described in terms of the entry of this the entries of this Cartan matrix. So in particular, one can use this loop presentation of the Yangian for a simple, finite dimensional simple Lie algebra and say, well, okay, now I will take exactly the same set of the same kind of presentation, but where I'm replacing a finite type Cartan matrix with a symmetrizable generalized Cartan matrix corresponding to a more general, possibly infinite dimensional symmetrizable Kac-Moody algebra. So I can take this long list of these infinitely many generators, this very long list of relation, and built by generators and relation, built out an algebra which I will call the Yangian of a symmetrizable Kac-Moody algebra G. So as you will see, this now becomes instead something a little bit artificial. Before for finite dimensional simple Lie algebra, the characterization of the Yangian was somehow very conceptual. And on the other hand, when you move to this Kac-Moody setting, is a little bit artificial. It's like, well, okay, now I'm taking the same relation, I move it here, and now I look at this guy and see what can I say about it. So, of course, I mean, one of the first questions would be, as we know, for example, that for Drinfeld Jimbo quantum groups associated to Kac-Moody algebras and so on, one can produce an R matrix. Here, in the same way, one can ask, is it possible somehow to generalize Drinfeld's theorem? Now, of course, I was insisting a lot on the fact that this definition is somewhat artificial, precisely because if you start like this, you will find immediately an abstraction. So, first of all, what I was telling you before was that this J presentation was precisely what was useful for constructing a coproduct. So when I do this, for constructing the coproduct, one interesting phenomena is that when I look at the loop presentation, then explicit expression of the coproduct in terms of this loop generator are not known and are not explicit in general. So, so in fact, even in the finite type case, there is a sort of a ping pong between this presentation that help you to prove properties of this algebra. In particular, whenever you want to look at the off-algebra structure, you need in fact to work with both presentations. Now, the loop presentation is what carries over to Kac-Moody algebras. So in particular, one of the first questions is, okay, so what about the rest of the structure? The presentation that I bring over, that I carry over, is useful for the algebra structure, but not for the co-algebra structure. So there is immediately somewhat of a problem with the coproduct. So I went indeed immediately to this step 2. So in fact, when you look at this Kac-Moody Yangian, one big issue is precisely given by the question, does the coproduct exist? Does it even make sense to talk about is there an R matrix or not? Okay, and so in fact, for an arbitrary Kac-Moody algebra, a coproduct has been defined in a work by Nicolas Gue and Nakajima and Curtis Pentland. Paper is quite old, even though it was published only in 2019. And so here also I'm writing something which is a little bit too restrictive. So what they really do is that they define this coproduct, but there are several things to notice. First thing is that this coproduct is not an algebraic coproduct, but it's generally a topological coproduct. So you need some completion of, you need to complete the space where you land. So you need to take this space and somehow take a completion. In a certain sense, it will mean, as I will show in a second, it means that you need to consider actually maybe series in a parameter with values in this tensor product. So you take something bigger. Okay, so this coproduct is topological, first thing, and then now we will discuss it a little bit more. And the second thing is that in fact this coproduct is only defined in affine type. Now this is not, as I said, entirely correct. So in two directions. First of all, is that they define a topological coproduct that depends, in fact, but their construction depends on an assumption, which is quite a natural assumption, which is whenever you take your Cartan matrix and then you look at all the submatrices of order 2, they all must be invertible. So it means essentially that your Kac-Moody, for example, cannot contain any SL2 affine. That somehow the two nodes of the linking diagram of the Kac-Moody cannot form any SL2 affine, for example. In fact, they cannot even form a Kac-Moody, an affine algebra of type A22 and so on. Okay, so the rank 2 minors must be, the order 2 minors must be all invertible. So in particular, this also means that even in affine type, their construction works for every algebra except those of rank 1, which are exactly SL2 affine, which correspond indeed to 2 by 2 Cartan matrices with determinant equal to 0. So those two cases, for example, are excluded by the construction of Guai, Nakajima, and Pentland. At the same time, on the other end, the construction with those two cases were analyzed and studied separately. So Weda proved that in fact there is a coproduct in type A22, and the coproduct in type A11, meaning in SL2 affine. It is unclear at the moment, meaning it's not in the literature. If you start looking, you won't find anything. In fact, the definition itself of the Yangian for SL2, of the affine Yangian for SL2, it is somewhat not, the original definition was not really the correct one. You need to adjust it. So it's a special case that needs to be treated sort of carefully on the side. And then I've been told that in fact maybe Schiffman and Vasserot they have a coproduct. They proved that there is a coproduct on SL2F on the affine Yangian of SL2, but this again is not out yet. I didn't see it, so I don't know. Anyway, point is, if we look at this affine Yangian, there is a tiny problem even at the level of coproduct. Most important thing though is that this coproduct is topological. Okay, so how do we deal with the fact that now the coproduct is topological, and so what do we want to show? What do we want to prove? So our setting will be the following. So we consider G an affine algebra, an affine complex algebra. For the reason I was saying before, in fact, we will exclude this type SL2 affine, and not really for the coproduct. As I said, this possible. This is probably an aspect that can be studied separately and probably adjusted. But as you will see in our proof, there is a much bigger problem with SL2 at. Much more serious problem. So we then denote by delta Z is this twisted coproduct defined by Guai, Nakajima, and Ventland. And then, as I was telling you, this is an algebra map that goes from the, in fact, we have series in the inverse, with values in the tensor product of the Yangian. And then by OYHG, here what I'm denoting, this is a category of representation of the Yangian. And then I will consider, in fact, these are modules over a Yangian, representation of the Yangian, such that whenever I restrict to the Lie algebra, one of the features that I didn't mention of the Yangian is that, in fact, the classical Lie algebra embeds into YHG. So in particular, I can consider a representation of the Yangian and then restrict it to the Lie algebra. And so what I want in this case is that this is a representation. When I restrict it to the Lie algebra, I get a category O representation for G. So by category O, this means in particular, this is a weight representation. So as a decomposition in weight space, weight spaces with respect to the action, the Cartan of G. Those weight spaces should be finite dimensional. And then there is a support condition, which is the usual cone condition given by Katz. So this is actually the category O, not the BGG category O, but it's the category O as defined by Victor Katz in Katz's book, for example. So said otherwise, I'm considering, in fact, category O representations of the Lie algebra that admits an action of the corresponding Yangian. Okay, so why do I want to consider now this representation? Because I was telling you before, there is this issue with this topological coproduct. So instead of working with these things sort of algebraically in this sort of clumsy setting, what I can observe is that if I take the twisted coproduct defined by Guai, Nakajima, and Ventland, then I can actually compute the coproduct. Then I can evaluate this coproduct on a tensor product of representation. And this Laurent series on this tensor product, in fact, becomes polynomial. So it just get truncated on any tensor product. And then I can now evaluate this coproduct at 1. So by doing this operation, this means that this topological coproduct that they defined is in a sort of said otherwise, is encoding a tensor product on this category of representation of the Yangian. Okay. So this category O for the Yangian does in fact admit a tensor product which I'm denoting by this tensor KM0. Now, why there is this 0 here? Because then what I will consider is a sort of a parameter deformation of this tensor product. Namely, I can define Vs to be the shift of V, meaning I'm taking V and then I pull back by one of these shift automorphism of the Yangian. And then I can define the tensor product of V1 tensor V2 at S to be simply the usual tensor product of V1S tensor Kac-Moody 0 V2. Okay, so this means what? That we have a category of representation, or this category of representation of the Yangian that admits a tensor product which depends on a parameter. In fact, it depends depends on this parameter polynomially. In fact. Okay, and so what do we want to prove? This is said in somewhat very fancy language. That this category O is a meromorphic braided tensor category with respect to this parameter-dependent tensor product that we just introduced here. Now, I want to stress that this is only fancy language, meaning it's just a sort of a way of concisely say, well, a bunch of list of relation, which I will tell you in a second, hold on in this category. The notion of meromorphic braided tensor category in this setting is not really given formally anywhere. The only reference that I know about this is due to a paper, an old paper by Soibelman, which is exactly meromorphic tensor categories. On the other hand, the setting that Soibelman uses at the same time is more general than we need, and still does not really apply to this case. So, in fact, it's not really a structure that has been studied, categorical structure, categorical framework that has been really formalized properly. Okay, so what do I mean by this? Is simply all the long list of relations that you will see below in a second. So this is indeed the content of our main theorem. So what we do is the following. So we assume to have two category or representation of the Yangian. And so what we will show is that there are two meromorphic functions. These are ida v1, v2. Ida is exactly this up and down. This is what denotes these two meromorphic functions, such that the up and down denote indeed the behavior of this meromorphic function, which is encoded by this first property. Meaning, as I start moving in the direction in the half plane, so I just look at S over H bar. And then I can consider essentially the half plane from a certain point on towards infinity in one direction or in the opposite direction. So as I move towards infinity in one of those two half plane, this meromorphic function is again isomorphic and tends to the identity as indeed this value goes to infinity. Okay, so here this epsilon eta that corresponds exactly to epsilon plus, epsilon up, epsilon down is just a sign. So it's telling you in which direction in the half plane you are going, parallel to the direction S over H bar. So here again, as you see, in this setting, really H bar is a number, and we really need it to be a number. So this is the analytic property of this operator, but then more concretely and related to the issue of finding an R matrix or not. And then what does this operator do? So first of all, I can compose the operator with the usual flip, and then this giving me in fact a Yangian intertwiner, which is natural in the two representation V1 and V2. That goes from the tensor product V1 tensor S V2 into this guy here. As you will see here, there is a sort of a game. First of all, we are flipping, so we are actually turning, going to the minus S, but then we need to shift everything by S, because in fact the representation that has been shifted is really V1, it's not V2. Okay, so it's slightly clumsy, but this is how you would read this identity. So the first thing, this is what first of all a meromorphic braiding would be. So a natural isomorphism between these two functors depending by this parameter S. And then these operators satisfy then two identities. First of all, as you probably imagine, this property 2 correspond to the intertwining equation of the R matrix as defined by Greenfeld, while this this property 3 instead takes into account what is the coproduct identities in this setting. So if I now take 3 representation V1, V2, and V3, then I can clearly consider the operator when the first representation is a tensor product, or the second representation is a tensor product. And then I get these two identities. These are indeed exactly the same thing that I was telling you before. If you take the original Greenfeld coproduct identities and you throw in a shift in the first term. Okay, so we get we have these identities here, and then again by composing, putting together these two properties 2 and 3, once again I get I can conclude that the operator R in fact is a solution of the Yang-Baxter equation on V1 tensor V2 tensor V3. Okay. Okay, so first thing, this is what these two actually, sorry, this okay, these three properties more or less is what you would call again a meromorphic braiding, but then we throw in some extra property that now correspond to the fact that this operator is constructed in a certain way and has a certain form, and this is also some property probably you have seen already other times. So the first thing is that this operator is shift invariant. So if I now take these two representations V1 and V2 and two scalar A and B, and then if I compute the R matrix on V1A and V2B, then this is the same operator when I'm just shifting the parameter S to by A minus B. And then now for the moment, we just have these two up and down, which are completely unrelated. They just satisfy separately all these identities. But then in fact, they are related to each other precisely by a unitarity condition, meaning if I take the up solution, so the solution with a certain asymptotic when I go at infinity, and then I consider the inverse of this matrix, this is related to the operator with the asymptotic at minus infinity computed at minus S. So this is now what is relating these two are matrices, which again are in fact going in two opposite directions. So it's quite obvious that by some sort of expected uniqueness, they must be related by something like this. And in fact, what also one can prove is that these two are matrices. When I consider their asymptotic expansion at infinity, in fact, they coincide. So this roughly means if you push it at infinity, then the operator you find at infinity is the same. So these two are matrices are not so different from each other. Not so much, in fact. So as we will see. And this property 6 that the two operators have the same asymptotic expansion at infinity. This actually comes to be quite useful when now we want to ask what about rationality. So here, if you see the statement of the theorem, the statement at the moment is we have a meromorphic R matrix. In fact, we have two meromorphic R matrices related to each other, but the two meromorphic R matrices, in fact, are well defined on any representation in category O. So I have no restriction. No, of course, there is no finite dimensionality. Remember that now in general, this guy would be pretty big infinite dimensional modules. And so, what can we say about rationality on the other end in this context? And then the interesting thing is that we get in fact a result similar to that of Greenfeld, but in a certain sense, this is a little bit more general even in this setting. So in fact, we look at two modules which are highest weight modules generated by two highest weight vector V1 and V2. And so in fact, in this setting, we can as well apply a normalization procedure on this tensor product V1 tensor V2. And this normalization procedure, which is similar to which is similar to what happened in Drinfeld, but only a little bit. This produced by normalization a rational operator. And moreover, this rational operator has an extra normalization condition at infinity. Meaning, if you take the limit for s that goes to infinity, then you will just find the identity. Okay. So let me comment a little bit on this. So the first thing is that indeed, if I really wanted to make a parallel with Drinfeld theorem about the existence of a rational intertwiner, Drinfeld theorem tells you there is a rational intertwiner whenever you work on a pair of finite dimensional irreducible representations. So first of all, there is the irreducibility condition, which in a certain sense we don't need. And the second condition is finite dimensionality. So if of course finite dimensionality for a simple Lie algebra correspond to integrable category O representation for a Kac-Moody. So it would be expected here, for example, to see the theorem for integrable category O, but in fact this is not really necessary. This sort of normalization procedure really can be done by relying only on this highest weight vector and the fact that we're working on highest weight modules. And then also again, so we have infinite dimensional stuff, not integrable, and also not necessarily irreducible. Still, we can. Well, sorry, this is not. These are highest weights, so they are okay. All right.
Yeah, can I ask a question?
Yes.
So maybe you already mentioned it, but I think I missed it in that case. So you said that certainly these vector spaces V1 and V2 are not necessarily finite dimensional, but
no.
How much of the finite dimensional modules are captured in this theorem? I mean, are all finite dimensional modules of this type, or this highest weight modules, or are they? Are they just trivial modules, or what is the?
You mean in the finite dimension? You mean in the simple Lie algebra case, in the finite dimension, in the finite type, or you mean in this setting?
In this general setting.
So in this general setting, again, if you imagine to consider, for example, category O integrable, except for trivial representation, all the other stuff are infinite dimensional, right? So most of this representation, generally, if you pick a random one, you will expect it to be very much infinite dimensional. Okay,
thanks.
So even in category O. Okay, so I mean, just generally in category O, you would expect it to be mostly infinite dimensional, and this is actually one issue. It is somewhat this is actually the main problem in producing an example, because in fact we are unable to give any explicit example of such matrices, because working with those representations in general is really hard. So they are massive, they are really big, and very, very hard to be described explicitly. So in this case, we know the stuff exists, we know how it behaves, but we don't know, we cannot tell you, yes, this is the formula of what we found. And this is sort of a tiny, not very tiny. This is quite a big issue. We're actually working on that. And the second comment that I wanted to do is that as you certainly know, like now a decade ago, a new theory of Yangians appeared due to Maulik-Kogunkov, and this theory of Maulik-Kogunkov includes also affine Yangians. The Maulik-Kogunkov affine Yangian is not exactly the Yangian I talked about, but the two things are quite similar. They are expected to share the same kind of representation theory. And on the other hand, Maulik-Kogunkov theory allow you to say, allow you in fact to construct R matrix, an R matrix, a rational R matrix, in the case of a rational R matrix for certain representations. Those certain representations, they are representation constructed via geometric methods. So generally, those are, in fact, so you will have these geometric Yangians acting on cohomology of certain Nakajima-Guyer varieties. So whenever your representation can be realized in this geometric form, Maulik-Kogunkov theory is giving you a rational R matrix. In particular, one of the behavior of Maulik-Kogunkov R matrix is this one. So when you go ad infinity, this operator reduced to the identity. This is quite a standard behavior. So first thing to observe is that our theory works much more generally, because of course you can feed, we can produce this R matrix on any category or representation. Also, generally, I think in Maulik-Kogunkov case, there is indeed highest weight irreducible condition, which in general we don't have. We have only the highest weight, but we do expect that whenever the two are supposed to be the same. To be honest, I cannot say it because this has been verified on some example. It's just we can say it because if there is some justice, they are probably bound to be related in some very strong way, even though it's not very clear how to prove it at the moment. So this is in fact at the moment the only hint that we can provide to say, well, you see, they have the same behavior. So this is again just to say that there is another theory on the table that does that. We do apparently much more in terms of representations. So okay, so how do we construct this operator, and what is the idea? What are the main ingredients behind this proof? Because clearly, essentially, the idea of the construction is in itself just already the proof of the theorem. Now, in order to describe the strategy that we apply to produce this operator, one should make another observation that in fact this category O possess another tensor structure, which is also a meromorphic tensor structure. So it's a tensor product that also depends on a parameter, and the dependence on this parameter now, on the other hand, is rational, is not polynomial. So there are poles possibly, and this tensor product is not always defined. So this tensor product is usually referred to as Drinfeld tensor product, and I will denote it by this tensor D, S. Again, this is a tensor product depending on a parameter. And concretely, what is this? Well, basically, this is exactly the same datum as saying I have a family of action of the Yangian on V1 tensor V2. This family of action depends on a parameter S, and the dependence on the parameter S, on the other hand, is rational. So indeed, there are certain values for which, for example, this action is not defined. So there are certain value S, probably a discrete set, such that in fact this tensor product is not defined. So the nature of this tensor product is quite different from the other one. The other one was in fact polynomial and always defined, and there was no issue. This one is somewhat more delicate. On the other hand, is more delicate, but is much simpler to describe because the formulae defining this action are much simpler formulae. Instead, as I was telling you before, if I want to consider the standard Kac-Moody tensor product, the formula for the coproduct in those cases is not really explicit, and so dealing with that is much more complicated. Here instead, Drinfeld tensor product has an issue because it's a topological, is also a topological coproduct, not really always convergent, but in fact with simpler formulae. Okay, so now in fact in our category we have two structures. We are really interested on the Kac-Moody tensor product, but we have an auxiliary tensor product given by Drinfeld. So how do we use this the interplay between these two tensor products? This is what we informally refer to as the abelianization method. Now it would be clear why this is called so. In which somehow we split the construction of the R matrix in two separate problems. And so the first thing that one tries to do is that, well, first of all, let's forget about the Kac-Moody tensor product. Let's focus only on Drinfeld tensor product. And let's see if I can construct an R matrix for the Drinfeld tensor product, which is, again, is a rational tensor product, but it's easier. So maybe let's try to solve the problem here. And then separately, I can ask, well, okay, but how does the Kac-Moody tensor product and the Drinfeld tensor product are related to each other? And so I can try to put the two things together and say, okay, maybe I want to construct a twist, Drinfeld twist, in fact, a meromorphic Drinfeld twist, which means, again, in all the cocycle identity that you have in mind, you probably need to throw in some parameter dependence that relates the Kac-Moody tensor product with the Drinfeld tensor product. If we assume that we solve these two problems separately, which you see actually they really don't talk to each other, they're completely separate problems that can be addressed separately, then I can put together this solution. So in fact, now what I can do is that I can construct an operator as I was looking for that goes from the Kac-Moody to Kac-Moody that pass to Drinfeld. So I go from Kac-Moody to Drinfeld, then to Drinfeld to Drinfeld, and then I go back to Kac-Moody. So I get this, I get my meromorphic braiding or my meromorphic R matrix as a composition of this one. Now, as you probably recognize immediately also by the symbols and so on that I'm trying to use, these in fact in finite type in a certain sense correspond to the fact that the R matrix of the Yangian, one can aim to produce a Gaussian decomposition as a triple product of a positive component of the R matrix, an abelian component, a zero component of the R matrix, and a negative component of the R matrix. So this was already conjectured by Koroshkin and Tolstoy in the 90s, that they conjectured that the R matrix of the Yangian possessed this factorization. And now what we're using here is that this Gaussian decomposition has in fact a categorical interpretation, and this is how this operator appears by precisely relating all these relating these two tensor structure on the same category. So what we get here is in fact an R matrix which by definition is given in a sort of a Gaussian decomposition form. Now, in fact, this kind of strategy and interpretation, now it's hard to give a fair genealogy of all this. As I said, probably everything goes back to Koroshkin and Tolstoy when this first appeared, this Gaussian decomposition appeared as a conjecture. The conjecture of Koroshkin and Tolstoy was recently proved and spelled out properly in a work by Curtis Pentland. But in a certain sense, this categorical interpretation of the Gaussian decomposition, which I think got already some insight on the quantum loop side in the work of Hernandez, but then was essentially spelled out in a work in 2017 by Sachin Gautam and Valerio Toledano Laredo. And then this same strategy was in fact used in a more recent paper by Sachin, Valerio, and Curtis, where they do it in order to provide a different realization of the R matrix of the Yangian of finite type. So the question is, okay, so that was already, everything was already done, the strategy was already there, all the ingredients were there, so everything would generalize easily. So, and this is absolutely not true. So this is actually how we started the project with Sachin and Curtis. We thought that essentially all the ingredients were already there, and so it would have been something very easy possibly very easy to generalize to the affine case. But instead, what is quite interesting is that instead this is not true. Nothing generalized to the affine case, and everything must be sort of reworked from scratch in order to be adapted to this new setting. So in this last 5 minutes, let me try to give you a rough idea of how the affine setting is actually very different from finite type, even though we are indeed recycling the same strategy used in finite type. So the most, I would say, the most innovative part of the story is the construction of the abelian R matrix. So the construction of the abelian R matrix for the affine Yangian is in fact something that relies on a difference equation. The very that this a combinatorial flavor. So in fact, we consider this difference equation that you see here. The all difference operator is here in green. The function that I want to find, lambda s, is here in red. And then this is somewhat the GS, is the constant term that then I need to, not constant, but this is what I need to find, is the constant term in the equation. So what is P? So P is a shift operator. Is simply an operator that takes a function in S and sends it to S shifted by minus hbar over 2. BP that you see here is in fact the quantum Cartan matrix. So what I'm doing is that I'm taking the affine Cartan matrix, I'm considering its symmetrized form, and then I'm replacing every entry in this symmetrized affine Cartan matrix by a Q number. The Q number is in fact not in Q as being a number, but in fact is a Q number at P, meaning I'm replacing it with the polynomial corresponding to the application of this shift operator. So this is what you will see here. Now is the determinant of this symmetrized affine P Cartan matrix as we call it. And then G, which is this constant term that then is used to produce, in fact, to eventually construct the solution lambda, is this big guy here. Again, there is the adjoint matrix of this P Cartan involved. And then this theta is this operator here, which is an operator where which is given by this element Ti R, which are in fact the generators of a commutative algebra in the Yangian. And this in fact is a huge, these are easy elements which are primitive with respect to the Drinfeld coproduct. Okay, so this is the difference equation that we consider, and then what can we do? Well, this a priori is completely algebraic at the moment, right? So this element here, this GS, I can think of it as something which is indeed is defined in YHG0 tensor 2. On the other hand, I can take this identity and then shoot it on a tensor product of representation, and then I can solve it there. So by taking the difference equation and go into a tensor product of representation, we now get a matrix difference equation there. We can actually decompose everything and looking at the matrix entries of this thing, and then we can use this the standard theory in difference equation to say, well, there exist in fact two fundamental solutions. So these two fundamental solutions has precisely this behavior as you go ad infinity in these two half planes that are quite far from the origin, but then again that ad infinity behaves in a certain way, and then we find the abelian R matrix as the exponential of these two fundamental equations. So very briefly, let me comment a second. First thing is that now you should see immediately why our construction does not apply to SL2 affine, because this difference equation completely collapse in type A11. So the determinant is equal to 0. So this equation is completely useless in that case. So, but only in that case. So there is only this SL2 hat case that we really cannot treat in this setting, and so this case has been studied separately by a PhD student of Sachin. And then the second question, which is of course is like where all this comes from, because at the moment is a little bit like black magic when you see it this way, and then here at the moment, I mean, my time is over, so I cannot say much, but the point is that although it looks so completely, so basically unmotivated, the point is exactly simply take precisely the intertwining equation determined by this condition. So you want this operator R0 to behave well and then to intertwine with the Drinfeld product. And so in particular, what you can do is just study how R0 interact with the Drinfeld product. You can look not at every element of the Yangian, but you can indeed look at this element in the commutative algebra. And then, as I was saying, these are particularly easy. They behave quite easily, quite nicely with respect to the Drinfeld product. And so you can say, what about I'm looking to find for an operator that behaves nicely with respect to this element, to delta S, delta D, to the Drinfeld product applied to this element. And then you see that, in fact, if you study this intertwining identity only for the commutative part, you will see that this already determines uniquely your matrix R0. And if you spell out this identity precisely, you will see that, in fact, this, if you look at how the conjugation by the R matrix works with respect to the delta of this element, you will see the quantum Cartan matrix to naturally apply. Having the Drinfeld product implies there is a shift involved. And so you will see that by, in fact, working out explicitly the intertwining identity of R0 with delta D of this element T, this sort of identity naturally appears. And then in automatic, you will see that if you do have a solution, this solution should be, if you do have an R matrix, an abelian R matrix R0, it should be a solution of this difference equation. And then you just work backwards. Very last comment. I did the story I simplified the story a lot, since something that was completely unexpected here was that, in fact, this difference equation is an irregular difference equation. So there is a problem here in when you go and expand in S inverse this operator G, and then you look at the vanishing order of this difference operator. So there is an irregularity. This irregularity in general will not allow you to solve this difference equation so easily by saying, there exist two fundamental solutions, blah, blah, blah. All that, in theory, you cannot do it. On the other hand, what is quite interesting is that the irregular terms on this operator G that appears, miraculously, they are central. And since, in fact, we are only interested in a sort of adjoint action of the R matrix, these central elements are not really relevant. So we can cut it out and regularize the difference equation and then use the standard theory to solve it. So both here and, in fact, in the story of R minus, which I don't have much time to tell, there are tiny little miracles appearing that somehow allow you to then solve the problem and then produce eventually this operator. But again, indeed, this part of the difference equation is somewhat quite obvious, the most interesting part of the proof. And then I stop here. Thank you.
Okay, thank you very much. Are there any questions or comments? Maybe online? Then I have a quick question about this special affine SL2 case, which you said Sachin's student has been working on. Do you get the same results there in the end, the same theorem?
Well, no. This is what he's aiming at. But the point is that exactly, you would like to apply the same kind of strategy. The real issue is not so you always look for this triangular decomposition or this decoupling the problem in two, and I think that there is no problem in producing R minus, meaning the other component, but indeed there is a big problem here. So here, in a certain sense, you need to proceed in a different way. But I should say this is a thesis project, and then it just started. So at the moment,
in progress. Okay.
It's very much in progress. Yes, it's very much in progress.
Could you maybe then kind of as a side or
sorry, just very one quick thing. This of course, it wasn't really in the setting that I explained, but as SL2 hat is somehow out of the game, and we are unable to say anything in that case. In the same way, also there is nothing we can say about GL1 hat. If anyone was sort of wondering.
Okay, and you mentioned several times kind of let's say analogies with quantum affine algebras or affine quantum loop algebras. Are there particular kind of explicit maps between affine Yangians and quantum loop algebras, or is it more like a philosophical analogy?
So in this case, actually, what you would see on the other side will be rather some quantum toroidal theory that you need to look at. So here we have, before I was doing the usual parallel between Yangians and quantum affine, and then now that you go one level up, you will have affine Yangians and quantum toroidal algebra on the other side. And now, quite interestingly, I think Andrea Negut gave a formula for the R matrix of toroidal GLN, which on the other end is very, very different from what we give. This story of sliced R matrices in terms of matrices of affine type and so on, but it's quite different. On the other end, Hernandez gave a formula for R0 in the toroidal setting. So a full R matrix is actually missing on the toroidal side, and there is only the abelian part. So our first question can be indeed if the two abelian R matrices can be matched. And this concern only the Drinfeld coproduct on both sides. On the other end, I don't think there is an analog of quantum toroidal to Yangian map.
Mm-hmm.
So clearly, probably there is something one should be able to compare, but it's not really clear. I would say, on the other end, this theorem somewhat suggests that even on the toroidal side, there should be a full R matrix available that can be constructed maybe in a similar flavor.
Mm-hmm. Okay.
But the
thanks.
story, yeah, I mean, the story from the point of view is very much open, I would say.
Okay. If there are no other questions, well, thanks again for this interesting talk. So let's close the session.